So please go ahead.
Okay, thank you. So first, I'd like to thank the organizers for the opportunity to give this talk. I'm really appreciative of this seminar, mostly not live, but using your recordings is a very nice service you're giving us. So thank you. So as Philip said, I'm going to talk about the symbol length of symbols in Galois cohomology. And I'd like to start with a quick introduction to this so-called Bloch-Kato theorem. So I'll start. Let F be a field. And for any two numbers, n and m, where the characteristic of F does not divide m, we can define a map called the norm residue homomorphism. So there is a map H, I guess the n is upstairs, and this will be here. It starts from the Milnor K group, modulo M, all the way to the Galois cohomology, Hn F, with let's say mu m tensor n. On generators, it does the following thing. So if you have A1 up to AN as an element, so when you apply this map, you get this so-called symbol element, which is, I like to think of it as cup product of A1 up to AN, where I think of the AIs as elements of H1. And the Bloch-Kato conjecture was that this is always an isomorphism, which we now know. But to make at least somewhat accurate history, I guess that the case where n equals m equals 2 was proved by Merkuriev. And then together with Suslin, they generalized it to any m, but n still has to be 2. In the case n equals 2 is due to Merkuriev and Suslin, and is well known as and is known as the Merkuriev-Suslin theorem. The general case, well, let's say if m equals 2, it's what's known as the Milnor conjecture, and this was proved by Verwotsky, and the general case again was proved by Verwotsky. And I should say with major contribution, in my mind at least, by Rost, with contribution by Rost, and probably I should mention Weibel as well, and Weibel. So this is a very deep theorem, and I usually like to see what I can do with this kind of stuff. So the main thing I've been doing through my entire mathematical career is basically asking the question of symbol length I got stuck on that. I'm not moving from that. I'm still stuck on it, but at least there are some results every now and then. So the main corollary I take from this is that the Galois cohomology Hn group F with mu m tensored n is actually generated by symbols. And again, by that I mean just cup products of your most basic elements. Like these are the most basic elements you can get in Hn mu m tensored n, like just cup product n elements from H1. Which in particular means that every element is expressible as a sum of symbols. So I'll just define once and for all what a symbol is. So definition, elements of the form, let's say this, are called symbols. And I like to denote it instead of writing every time cup product, I'll just do something like this, A1 up to AN. And I would like to add some index to it, let's say M, to denote the fact that it's coming from Hn F mu M tensored n, like the degree of the root of unity that we're using. Okay. So what is the symbol length question? Let's talk about the symbol length. So let P be a prime. Different from the characteristic of the base field. And let T be smaller than R, just two integers. Then we have a short exact sequence of Galois modules. Goes like say 1. Yeah, by mu m I mean just the group, the roots of unity in some fixed algebraic closure. So I'll write it as mu, sorry, p to the t tensored n, u p to the r tensored n, u p to the r minus t tensored n goes to 1. The second map is just the usual projection, and the first map is just multiplication by p to the t minus to the r minus t. And this exact sequence induces the following, inducing the following part of a long exact sequence. The part I'm going to use is going to denote it as 1. It's going to be Hn Hn u, oh, not r, it's p to the r, and here it's p to the r minus t. Then I'm gonna give these maps like just some kind of notation. Just to make sure we understand what these maps do, I'm gonna tell you what it does to symbols. Okay, so if you have a symbol, the right map and psi and m of some a1 up to an p to the r, it comes from the middle, is just the same symbol, only with lower degree. And the left map, again, if I'm going to take just the symbol of degree p to the t, it will just be, well, p to the r minus t times the symbol a1 up to an of degree p to the r. Okay, so if you like symbol algebras, then this really makes sense in terms of degrees. I will talk about it maybe later for a minute or two. So what can we say? We have this exact sequence, and we know that if an element is in the kernel of the right map, it has to be in the image of the left map. So this is what we mean, and the left-hand side is generated by symbols of degree t, p to the t. So this will mean the symbol length of degree p to the t. So definition, let alpha being hn just an element in the middle. We'll say it has a, we say alpha has effective exponent p to the t, and I denote it as effective exponent of alpha equals p to the t. If t is the smallest such that c and p to the t of alpha equals 0. So the reason I'm using the notion of effective exponent instead of just saying exponent is because they're not the same. Actually, exponent p to the t is weaker than effective exponent p to the t. I actually have a proof for this weird notion, but it's not my proof. You can find it in one of the later works of Szywatsky. And everything has to do with some connecting map disappearing or not. In any case, if you like just exponent, just add all roots of unity to your base field, and then the effective exponent and the exponent are the same thing. Okay. So what is the symbol length question? So symbol length question, definition, or maybe question. It just says the following. So again, let alpha be a class in this in this group with effective exponent, say p to the t, then the symbol length of alpha is the smallest number such that we can write alpha as a sum. So in our case, it will be p to the, okay, let's say p to the r minus t times the sum of symbols alpha I, or alpha i's are in h and f u p to the r tensor then. Okay, so we know if it has effective exponent p to the t, it's in the kernel of the right-hand map in the exact sequence. So it has to be an image of something from the left-hand side. And this is exactly how the images look like. And the number of symbols needed are what you call the symbol length. And I'll denote it mostly as let's say the absolute value of alpha is at most n, okay, or equals to n in this definition. It's just n. So I hope at least you got the idea of this question. And I'd like to focus a little bit on the case n equals 2, because that's like the main focus of attention, as we can sometimes at least identify the second cohomology group with some part of the Brar group of the field F. So the case n equals 2 and I'll assume just for simplicity that whatever roots of unity I need are in the base field. So what happens here? First of all, under these assumptions, the regular exponent and the effective exponent are the same. And we have that h2 f u p to the r tensor 2 is the same as just h2 f u p to the r, which is isomorphic to the p to the r torsion part of the Brar group for base field F. So this makes the question a bit more concrete, at least in my mind, because you can start working with algebras and trying to express them as tensor products of specific kinds of algebras, which are called symbol algebras. So symbols correspond, in this case, a symbol, let's say AB, P to the RF, corresponds to the symbol algebra it's also denoted like this, ABF. And just to show you that this is actually an algebra, I'm gonna write down what it is. It's just F adjoined with two indeterminants, X and Y, such that X to the P to the R is A, Y to the P to the R is B, and YX is rho XY, where rho is a fixed generator for the group of roots of unity of order P to the R. So the question here becomes, given a class in your Brar group, the notion of exponent is well defined, and if you have, so suppose your degree P to the R and you have exponent P to the T, by Merkurjev-Suslin, you need to be expressible as a tensor product of symbol algebras like these ones, only instead of P to the R, you need to have P to the T as a degree, okay? As far as I know, most of the results known are on this are in this case, in the case of n equals 2, and I would just like to note that, notice that if you have AB of degree p to the r over f, and you tensor it with itself p to the r minus t times, what you get, well, in the Brauer group, it's equal to the class of the algebra AB p to the t over f. Okay, this is not that easy to show. In fact, using just algebras, I mean, it's not hard, but you can get it like for free using these kind of notations with these twisted roots of unity things. So I'd like to give just a couple of like known results. Basically, my favorite one. So known results, like examples of known results. There are many other results. I'm not even gonna say that I know all of them, maybe most of them, but well, my favorite one is due to Albert. And this just tells you that if A is a F central simple algebra of degree 4 and exponent 2, then A is actually Q1 tensored with Q2, where Q1 and Q2 are quaternion algebras. So in this case, it's actually isomorphic because the degrees match, but in general, it won't be an isomorphism. It will just be equivalent in the Brauer group. The second most, well, the one that I don't think I can leave out is just the Albert-Brauer-Rasse-Noether theorem. And this just tells you what happens over number fields. So if F number field, then any central simple algebra of exponent, say M, is equivalent to one cyclic algebra. In Brauer of F. So cyclic algebras are just simple algebras when you don't have roots of unity. You can still define some kind of special types of algebras. And I will not say any more about the case n equals 2. Maybe it's probably the only two results I know about higher cohomology. I'd just like to mention them. These are results by Parimala and Suresh. I believe Suresh spoke about one of these results in this seminar, actually. And what it says is that it says the following: assume F is the function field of a curve over a p-adic field. This case is due to Parimala and Suresh, or a number field This is by Suresh. And assume also M is a prime. And M is in your base field. Then every element in H3 FUM is one symbol. This is very strong and very nice, I think. Lastly, I'll say that Saurabh Gusavi very recently, I think from the last year, he just removed some of the assumptions. He removed the assumptions. First, that M is a prime. So M need not be a prime. And he removed also the assumption that mu M is in your base field. And still the result holds. The results of Parimal and Suresh, which is very, very nice. Okay, so now I'd like to give you the real motivation for this project that I started, which is a theorem of Tignol from around 83, if I'm not mistaken. So here is a theorem by Tignol. I think the paper is called Cyclic Algebras of Small Exponent. And the result says the following. Let A be a cyclic algebra of degree p to the r and exponent p to the t, and assume mu p to the t is in our base field. So this assumption tells us, at least by the Merkurjev-Suslin theorem, that A needs to be a product of cyclic algebras, of symbol algebras of degree p to the t. And the exact number he got is the following. Then the symbol length of A is at most p to the r minus t. So if you add all roots of unity into your base field, say all mu p to the r roots of unity, then the theorem tells you that if you have A, so A being a cyclic algebra now means that A is actually something like this, degree p to the r over f. And his theorem tells you that you can write it in the Brauer group as the tensor product of p to the r minus t algebras of degree p to the t. This is very nice, and it's quite a short proof, and I really liked it. And for a long time, I was thinking that I can do something with it. And finally, I was able to do something which relates to it in a way. And so my main motivation was to generalize this theorem, namely ask the following question. Here is the question I have. So let alpha be any symbol B of effective exponent p to the t. What is the symbol length of alpha? So of course, Tignol's result says that if n is equal to 2 here, then we know exactly what is the symbol length, or at least an upper bound, which I believe, I'm not sure, but I think it's sharp, but I'm not sure. It's p to the r minus t. That's at least an upper bound. And I would like to tell you what are the possible answers that I got in this on this question. So here are some answers. So the first answer is that Tignol's theorem works in this case as well. So basically what I'm doing is working in K-theory, and he was working in the Brar group. There is a little gap which only exists when you don't have enough roots of unity, but still it's a new case, and his proof actually works exactly the same with a little bit of minor modification, but Tignol's result is the same. So if n equals 2, Tignol's bound, let's say, holds. Second thing I'd like to tell you, what happens when p is 2? So one might think of it as the case of Pfister forms, or like higher things related to Pfister forms. So if p is 2, characteristic is not 2, and alpha is a symbol in Hn f mu 2 to the r, of effective exponent dividing 2 to the r minus 1, that's all I can do. I can't do a general t smaller than r, just t equals r minus 1. Then I can show that the symbol length of alpha is at most, what is it? Yeah, 2 to the n minus 1. The proof of this is really using Pfister forms. It's quite basic if you know the theory of quadratic forms, but it was nice to write it down like that. In this case of p equals 2, I can also do something a little bit more. In this case, using a chain lemma, I'm going to write it with these guys because it's not the usual chain lemma, but we adapted it somehow to get some kind of a chain lemma. I was able to use this to bound. I should say we can bound. Maybe say that if alpha is the sum of two symbols, let's say alpha 1 plus alpha 2, alpha I symbols, let's say of degree p to the r, and the exponent and effective exponent dividing, not p, it's 2, r minus 1, sorry. Then the symbol length of alpha is at most 2n minus 1 times 2 to the r minus 1. 2 to the n minus 1, sorry. So you have to do it like, you have to add 2 to the 2 times n minus 1 and multiply it by the previous bound. So that was 2. The third thing I want to tell you about is what happens for any degree. So let's say the case n is smaller, greater or equal to 3, and assuming f is what you called prime to p closed, namely any finite extension of f is of degree p to the something. There are no prime to p degree extensions, field extensions. And characteristic 0. So if alpha, so let again alpha hn f p to the r is a symbol of effective exponent dividing p to the r minus 1, then the symbolance of alpha is at most p to the n minus 1. In order to do this, I'm using the so-called norm varieties defined by Rost, and in particular, I'm using the hypersurface representation of this, of one possible norm variety for a symbol, and just doing the computations. So basically, it's not my theorem; it's like an immediate result of Rost's work. But here, the main difficulty from my point of view is that I need f to be prime to be closed. So the next thing I was doing is I looked what can I do for n greater than 2, but still remain over my base field, and that will be the case of n equals 3. So if n equals 3, and I guess I'm assuming that rho p is in my base field, so mu p is, let's call it mu p, is inside the base field, and alpha is again, as always, a symbol in H3 this time, yeah, sorry, H3F UP tensor 3 P to the R tensor 3 with effective exponent dividing P to the R minus 1. Then I can express alpha using co-restriction in the following way. Then alpha can be expressed as, let me get this right. So alpha equals P times the sum up to P of alpha i's, which alpha i's are symbols, plus, let's say it like this, P times the sum I equals 1 up to K of the co-restriction from some fields. I will say something about them. Ti to F of a sum j equals 1 up to P gamma j's. Again, these gamma j's are symbols. The reason I'm writing it like this is in H3 or in K3, we don't have this Rossett-Tate thing that tells us exactly how many symbols you need to express this co-restriction. So the main, in order to get a real bound, I needed to compute the co-restriction basically from K3 of a field extension. So just let's say something about these fields, Ti's, the sum of their degrees is at most p minus 1. And the worst case is when we only use one T. That is, we're doing co-restriction from a very big field extension instead of splitting it to a few co-restrictions, but from lower field extensions. So if K is when K equals 1, and then alpha is just, let's write it as P sum alpha I plus P times the sum J equals 1 up to P of a co-restriction from T to F of gamma J's. Again, gamma J's are symbols, and the alpha I's are symbols. And the dimension is T over F is exactly P minus 1. So it turns out that taking co-restriction is a very expensive operation in terms of symbol length, at least from what I can compute, at least. It's not by no means it's optimal. It's just an initial computation. I already have some new ideas as to how to do it with less symbols. But what I can for sure say is that the following. So in order to get a bound, actual bound, one needs to get a Rosetate kind of theorem. So as I said, what I can do now is at the moment, I can say the following. So write AN for the number of symbols for the symbol length of the co-restriction from K to F of an element ABC in K3, where K over F is N. So how many symbols do I need in order to compute the co-restriction from a degree N extension? Then I got this recursive relation that AN is N plus N times AN minus 1. And I looked it up. It's called, if you want to write it as an explicit thing, it's a sum of the following factorials. I don't think there is an exact formula for it, but asymptotically, it's supposed to be what I saw online is that AN is approximately E times N factorial minus 1 minus O of 1 over N. So it's quite close to E times N factorial, which shows you that you really pay a lot of price if you take the co-restriction from a big field extension. So whenever you can like split it into sums of co-restrictions from lower field extensions, then you'll get better bounds. So if I plug this into this presentation that I gave before of how you can express alpha in the worst case, then what you get is that the symbol length of alpha from above is at most AP. Okay, which means again approximately E times P factorial. Let's say, okay, -1. Yeah, so these are the results. I'm not going to prove all of them. What I would like to show you is how you can really generalize Tignol's argument easily, really very nicely to this higher cohomology setting, but you get not as good bounds as I've told you now. You get a bit higher bounds, but still the method is, I like it. So I would like to just give as an example some kind of a proof of something. So let's do example, say NB3. So we'll get out of our comfort zone from H2. Let's go to H3. And suppose you have ABC P squared and with effective exponent being P. So how many symbols do we need of degree P do we need? So what that's my understanding of Tignol's argument. I'm not claiming that that's how he sees it, but that's how I understood his work. Then you do the following. What does it mean for the effective exponent to be P? It means that ABCP is trivial. But in this case, we have a theorem by Merkuriev that tells us exactly when a symbol of degree P is trivial. It's exactly, well, I'll just use one side. It means that, for example, C is a norm from the cyclic algebra AB. So C is actually a norm from some field extension where what is this field extension? K is a degree P splitting field of the algebra ABP. Okay, it's just the usual criterion. When you copy something from, when you copy a symbol with an element from H1, it's trivial when exactly that H1 element is a co-restriction from a splitting field of your symbol. The nice thing is that it works over your base field, and you don't need to go to prime to P closure of your base field. So what does that tell us? So we can do now a little computation. Can say ABC P squared is actually AB norm from K to F of some K, P squared. And this is now by the projection formula, you can just take the norm outside. You can write this as co-restriction from K to F of AB K, P squared now over K. And now what you need to notice that the symbol AB P squared has effective exponent equals P. And this is quite clear because indeed ABP over K is trivial because K is the splitting field for AB over F. So ABP over K is trivial. So the effective exponent of AB P squared is P, which tells us by assumption on K. So what this tells us is that you can write it as the co-restriction from K to F, and instead of one symbol, you will now have a sum of P symbols A, B, AI, BI, CI. So I'll write it like this. So the symbol length of ABC is at most P times the number of elements you need in order to compute a co-restriction, which comes to be P times AP. And the way I computed it, this is just, that's done, that's it, nothing more to do. That's very nice closed argument by Tignol that works. But the bound is P times AP, and the bound I got, but using twisted polynomials, I got that the bound is at most AP. So it's better. I'm not sure how much better, but it is better. So you can write it down as a new result. In any case, that's all I wanted to say. Thank you very much.
Okay, thanks a lot. Questions or comments?
Are there any techniques for proving lower bounds on the symbol length?
That's a good question with no good answer in my mind, at least. I mean, the minimal one is like just the number of, I don't know. I won't even try, I guess. I'm not sure. Maybe cohomological invariance or stuff like that, but nothing that I know about.
Not even essential dimension?
Yes, something like that might work, actually. Yes, that's true. If you know the essential dimension is not 2, for example, it can't be 1. So, but really, lower bounds, I think, are very hard.
Okay, so I have one question. What about specific fields?
Yeah,
Suresh and others. Yes.
So I'm a general field kind of guy, and I really don't think about special fields, because if it's not general, well, I don't know enough about special fields, so I only work with general fields usually. I'm sorry. Don't mean to offend
okay.
anyone.
No, maybe no, because we at the beginning you mentioned them, and then they totally disappear.
Yeah, because these are like big results in my mind, like these special fields, number fields and like curves or periodic fields and stuff like that are like fields of general interest. And I mean, the methods used there are completely different than what I'm doing. I'm just doing like generic computations, and what these guys are doing are more geometry or maybe arithmetic geometry. And I'm still learning. Maybe in the future, I don't know. I'm trying to learn these things.
Other questions? Well. Okay, so before thanking the speaker, I would like to thank Cameron Rutter. We did manage very well with the Zoom we Zoom
Thank you,
things
thank you.
today. Okay, thanks a lot, and thanks to the speaker. And we resume in 1 week, same time. Okay, bye.
Bye. Thank you.